Okay, this month we are taking a look at the curses library for character-oriented screen applications. We will let's take a look at the history of curses. So when Bill Joy created the VI editor in the mid-70s, he was using a serial terminal, a CRT serial terminal, a Lear-Siegler ADM3A, and he wanted a visually oriented editor for his screen terminal compared to line-oriented editors that were common at the time that people used with teletypes. So he initially hard-coded the particular escape sequences for the ADM3A into VI, and people saw the editor. He shared it around with some people, and they liked it, and they wanted to run it on their terminal. So he extracted a database of escape sequences that mapped to specific abstract operations, like move the cursor to this location, or erase from the cursor to the end of the line, erase from the cursor to the end of the screen, so on. And that mechanism of abstract terminal operations mapped to a database of escape codes became TermCap, the TermCap library. This was later rewritten as a term info library for System 5 Unix at AT&T. But TermCap is the low-level mechanism of, you say, I want to do this operation. You look it up in the TermCap database, and it tells you these are the escape codes that correspond to that operation. And there's a bunch of low-level details in there, like certain terminals, it takes time to perform a certain operation, and they can't respond while they're doing that operation, so there has to be a certain amount of pad bytes that are sent to the terminal. You normally don't notice these things in a modern environment because you're using a terminal emulator and everything is so fast that there's no padding necessary. But if you're talking over a high-speed line to a slow terminal, you need those details, and that's part of what's in TermCap. Ken Arnold borrowed the screen manipulation code from VI. So VI had within it the idea of, like, here's this screen, and I want you to update the terminal to reflect what this image is in memory of what I think is on the screen. But all that was available so far was the low-level TermCap library that just gave you access to the escape sequences. It didn't give you things like, an abstract operation like insert 3 lines here. So Ken Arnold, that code was part of VI, but it wasn't available as a separate library. So Ken Arnold borrowed the code from VI and created the curses library API, which is a high-level oriented library of things like I said, insert 3 lines here, scroll 3 lines over there, so on. And that's layered on top of TermCap. Curses is an immediate mode style library. It's not event driven. So if you're used to old style DOS programming, this will feel very familiar. If you're used to, a modern windowing system, you have to remember that, everything happens kind of immediately. There's no event dispatch, and there's no framework that takes over the main part of your application. So it's up to you to write all that. And Curses only handles screen I/O. It doesn't handle things like, if you're talking to a real terminal over a serial line, there's other things that need to be configured, like the baud rate of the serial port, how, if parity is being used, what form of parity, and so on. Curses doesn't handle any of that. That's all up to your operating system. Operating systems provide APIs to manipulate those things, but Curses doesn't get involved with that. Curses handles everything by the idea of a virtual screen update. So the application writes to a buffer in memory, that's the virtual screen, with API commands, and then issues a call to a refresh function that sends the necessary escape sequences to the terminal to make the physical screen reflect the contents of the virtual screen. And Curses attempts to send the minimum amount of escape sequences to achieve the refresh of the physical screen. And as I say, in a modern environment, we're using a terminal emulator. Things happen so fast that you don't even notice what's going on. But if you're dealing with visual refresh over a very slow connection like 300 baud, that's 30 characters per second, the more efficient it is at sending escape sequences to update the screen, the more you're going to appreciate it. And initially, VI was developed in such an environment, 300 baud modem connection to a remote machine. The implication here is that instead of just blasting out, an 80 by 24 set of strings to, if supposing your screen is 80 columns by 24 lines, which is very common for a physical terminal, but for a virtual terminal, they're typically larger. Instead of writing every character out, you tell curses what you want to have done. So, scrolling, inserting, deleting. You try to express the operation at as high a level as possible. The typical program loop for curses is you do some configuration of the library. We'll see some examples of these kind of configuration calls. You call initScr, initScreen, to initialize curses, and that creates a standard screen that corresponds to your kind of default I/O space. And then you enter, if it's an interactive program, you're entering some kind of main loop where you're reading input, you're updating the virtual screen, you're calling refresh to get the physical screen updated from the virtual screen, and you keep doing that until the input conditions, they type Q or something to indicate that they want to quit, and then you call endWin to close down curses. Now, curses has been around a really long time, and there's a few things we've learned about libraries since then, like all the API functions in a library should begin with a unique prefix or something like that. So or in C++ terms, they should be in a namespace so that they don't collide with other functions that might be in the application. Curses predates all that, so there's no unique prefix on all the curses API functions. initScr, refresh, endWin, they're all just whatever they are. The standard screen, which I mentioned, once curses is initialized, it provides the standard screen, which you can reference explicitly through the variables studscr. And if you need to call a function that takes a window argument, it's actually a pointer to a window structure. This is a C-style API after all. You can use studscr if you want that to take, want the operation to apply to the standard screen. Now, there's also these global variables called lines and calls, and these, although they're in caps, you might think that they're macros. They're the names of variables. And when you initialize curses looks at in a Unix environment, it looks at the term variable and uses that to look up all the entries in the term cap database, and the term cap database says how many physical lines and columns are on the screen, and that's used to populate lines and calls. If you're running in a terminal emulator, Xterm, or as we will see later, the Windows console, lines and calls is updated to reflect the size of your window as opposed to the size of the physical screen. But if you're talking to a real terminal, lines and calls will be the physical lines on the screen, which is typically 80 by 24, 80 columns, 24 lines. Your terminal may support various optional features, and there's functions that you can call ncurses to see if those features are present. Things like, does the terminal support color? Does it support a particular kind of attribute? We'll see an example of some of these functions. And you perform basic I/O operations, and they all operate on standard screen. Usually these functions are just macros that invoke the windowed function with the standard screen variable supplied as the argument for the window parameter. So what's in a window? Well, it's got a rectangular array of characters with attributes. It has the idea of a current cursor position, and it has optional features as I mentioned that correspond to the terminal. Now, everything we're going to do is talking to a single terminal, but it is certainly possible with multiple serial ports attached to a machine, each of which is attached to a terminal. It's possible to open those serial ports as files and create a curses connection to those terminals so you can talk to multiple terminals through multiple windows. And in which case, the different windows would have different capabilities because they're different physical terminals. I can't imagine anybody doing that these days unless they just want to have like a vintage programming fest kind of, you know, fun thing to do just because they can. But it's more typical that you're just dealing with a single physical device. It may have multiple windows mapped onto that physical device, but so typically they're all going to have the same features. So I mentioned attributes, but I haven't really explained what they are. So attributes specify how characters appear on the screen, and these are typically things like underline or blink, or sometimes there's a dimmed out low intensity way that you can draw a character, or the opposite, a bold way that you can draw the character. You can draw it with inverse video where the foreground and background colors are flipped. There's also for terminals that support color, there's the idea of a text background and foreground color that you can apply through attributes. Your typical output operations are going to do things like move the cursor to a specific location and then put some text there or move some text around, or various things. For output, you're going to be adding a single character or adding a string or doing a printf style at the cursor location. And after you perform these output operations, the cursor position is advanced accordingly. And that means that if you try to write past the end of the right-hand side of the window, the default behavior is to wrap around and go to the first column of the next line in the window and continue outputting characters. That can be changed, but that's the typical thing, which is typically what you want. Similarly, if you write past the bottom of the screen, then the screen will be scrolled up and you'll get a new line at the bottom that's empty, and you'll continue writing down there. So things like new line characters and tab characters are respected when you output them into the virtual window, so that if you do add ch to add a single character and the character is new line, then it moves the cursor to the first column of the next line. If you are doing input, you can do blocking IO with get ch. The default behavior is blocking. Gets a single character. If you want to test if a character is waiting without blocking, you can turn off the blocking behavior with no delay and then call get ch. And if there's a character waiting, it gives it back to you. And if not, it gives you a sentinel value that indicates that there was no character available. Typically, or by default, input characters are echoed on the screen at the cursor location when they type a character. This is usually what you want. If you're filling out a form, you want the user's input to be echoed. But if you're doing something else, like a game, something like that, you don't want to echo the input, so you can turn the echo off. You can get an entire string. And again, this is an old C-style API, so they just assume that the output buffer, which you supply as a pointer, is big enough to hold whatever string they type in. You can use get nstr to fill a bounded buffer so you'd avoid any potential buffer overflow problems. You can combine cursor move with output by just using an MV prefix and supplying the row and column. So in curses, everything is row and column. A row is the y coordinate and a column is the x coordinate. So if you're used to xy Cartesian things from geometry, just remember that in curses it's always yx, it's always row column. You can have multiple windows where you can position a window data structure for different regions of the screen, so you can update different regions of the screen independently in a convenient way, and then just call refresh and have them all copied to the physical screen. And a window's contents are not displayed on the physical screen until refresh is called. Distinct windows have distinct, buffers in host memory to represent the contents of the screen. If you want to share the same buffer using a window data structure, then you can create a thing called a sub-window. That's kind of an advanced feature. We won't be talking about it other than mentioning it now. And a window is limited to the size of the physical screen. So you can't make a window bigger than the screen, bigger than lines and cols, those variables that tell you how big the screen is. However, there is a thing called a pad. A pad is similar to a window. In fact, when you create a pad, it gives you back a window star. But pads exist only as a virtual screen buffer in host memory, and they can be of arbitrary size. So they're not limited to the dimensions of the physical screen. You can create a large pad containing a bunch of stuff. You write it into the pad. Now you've got the virtual buffer associated with the pad filled with the content that you wrote into it. And then to get it onto the screen, you do an operation to copy a subregion of the pad onto a portion of the screen. We'll see that. I've got some example code that shows you how to use a pad. There are two prominent implementations of curses that are in use today. If you've got actual vintage Unix machines, they probably shipped with a curses implementation, either a BSD style implemented on term cap, or a System 5 style implemented on term info. But either way, the curses API is the same. Modern Linux uses an implementation called ncurses. This is an open source implementation. It is stable and under active development. The guy Thomas Dickey that has created is the maintainer, and I believe he's the original author as well of ncurses. He's constantly applying little bug fixes and things like that. There's also with ncurses some additional layered libraries that are useful for things like forms and panels. We're not going to talk about that today. I just mention it. And it's available through standard Unix package managers. It's also available through vcpkg for your Linux build. On Windows, there's an implementation called pdcurses. That's public domain curses. It's been around, again, a long time. It originated with DOS so that people could take curses-based applications and get them running under DOS. Curses is a good fit for DOS because it's not, there's no event dispatching or anything like that. It's all immediate mode, so it works just fine in a DOS environment. pdcurses is Windows only. It is also stable and under active development, and it is also available through vcpkg. Both of these libraries provide the core curses API. They both have extensions that are specific to that library. So when you're, trying to do something, just consult the header file for the functions that you're calling to see if they're specific to one flavor of the library or the other. pdcurses does have some ncurses APIs implemented in it, mainly the mouse API that allows you to use a mouse to interact with a curses application, which for a actual physical serial terminal wouldn't be likely, but for a modern windowed environment where you're running a terminal emulator, that's pretty likely. So check the header file there for stuff there that you may want to use. Okay, let's take a look at this sample code. Briefly, we'll just take a look. There's this is invisibleisland.net. Let's make that a little bigger. This is Thomas Dickey's website where he's got, frequently asked questions, other stuff like that about ncurses, and pdcurses.org is the public domain curses mailing list. They have a repository on GitHub, and you can see that if we look at the commits, most recent commit was 5 months ago. So both are in active development. Okay. So over here, let's make this a little bigger. And we'll move this over so you can see it. Let me go turn off some debugging that I had on there, just to show you what this looks like. So here's this little animated Christmas card that I created. Because I had some things were slightly out of date, so it's going to build. All right. So it has two phases where the first phase, it scrolls this Merry Christmas message down. It scrolls it 3 times. The second and third time, it's colored in green and red. So here's the third time. And then we switch into another Christmas greeting scrolling, this time scrolling off to the left. And that scrolls 3 times as well. Just let it go off the screen here. And you see then it restarts. I'm going to quit by pressing Q so we can look at some code. The code pretty much has a sorry, didn't want to cough on stream. Okay, code just process main function just parses builds a vector of string view for the arguments and then delegates off to a library function. If we drill into this library function, it does some argument handling and then initializes curses. Here's one of these query functions I mentioned. The has colors returns true if the terminal we're using supports color. To begin doing color things, we call start color. And then I've created 2 color pairs. So a color pair is a combination of a foreground and background color. So this is red on black and green on black. So that sets up 2 color pair 1 and color pair 2 for me to use. I'm specifying whether or not the cursor is going to be visible. I did that by creating my own little enum here that is either the cursor is hidden or it's shown in normal style or it's shown in standout style. Standout style typically means a cursor is a block instead of an underline. So we're going to set the cursor visibility. We're going to say non-blocking I/O on standard screen. And we're not going to echo input on standard screen. And we're going to enable scrolling on standard screen. And here's my 2 little, I've got this abstract interface here for a renderer that says how many frames it is going to render, and then there's a render function that's called for each frame. And I've got 2 of these, one that shows that Merry Christmas scrolling vertically in a Gothic font, and the other one shows Merry Christmas scrolling horizontally, and the Merry Christmas message is wider than the screen. You could make your screen really wide, but the way I've coded it, I've assumed that it's wider than the screen. My terminal window is 120 columns wide, which is pretty wide, but still this message is wider than that. If I wanted to make this code more robust against really large virtual terminals, I would do some more checks against lines and calls, the dimensions there, to make sure that the effects that I'm doing make sense. But, you know, we're trying to show you how to use the library here. We're not trying to, you know, ship a product that somebody's going to pay money for. Now here's my animation loop. And there's a bunch of fiddly little details in here, but basically all you need to know is if when we run this, we can press space to pause the animation. We can press S to go into single step mode, where every time I press space it will advance by one frame only. Or we can press Q and it'll quit at any time. Or if the animation runs all the way to the end, then it exits all by itself. It doesn't repeat indefinitely. But it shows those two effects. It scrolls vertically 3 times that message, and then it scrolls that second message horizontally 3 times. And then if you haven't pressed Q by then to quit out, it'll quit on its own. So this is just my little animation control loop here. And you can see here's an example where I'm moving the cursor to a certain position, and then I'm doing an operation. In this case, I'm clearing from the cursor to the end of the screen, because this is the point where I switch renderers. So in between renderers, I'm going to clear the whole screen so that whatever was left on the screen from the previous renderer, the next renderer doesn't need to know about that in order to clean it up. We're just going to clear the whole screen. So very simple. If we take a look at these individual renderers, so here's my Gothic font Merry Christmas message. If you're wondering how I generated these text strings, there's an open source program called Figlet that has the idea of a character-based font, so it makes up a character glyph from a bunch of other characters. So it has, in this Gothic font definition, there's a definition for a capital M, and this is what it expands out to. So I just ran Figlet to generate these, and then I captured them as raw string literals. That way, if there's backslashes used, I don't have to worry about doubling up the backslashes or anything like that. A raw string literal ignores everything between the delimiters. My delimiter here is capital R quote sprite open paren. So I've got my sprite, and I've got 2 different ways to render this based on different strategies. So right now I'm defaulting to this scroll strategy, but there's 2 different ways that I've implemented drawing it. And the first one is I'm just going to redraw everything. Pardon me. So you can get some frogs out of the throat there. Okay. So the first strategy is we're just going to redraw everything. And you can see there's a lot of bookkeeping. I have to figure out beginning and end, and I have to figure out when to switch from the red color to the green color. And at a certain point, after I've done my little bookkeeping thing, I'm going to do the move and add string. And again, it's row column, not XY, it's YX. And I'm going to add that text to the screen. And I'm going to, every time I add text, I'm going to turn off the color attribute by setting the attribute back to normal. So for attributes, the way they work is, where did I turn it on? Add or set. Okay. You call it add or set, and then all the text that you add to the screen from that point forward is using that attribute. So turn the attribute on, add the string, set the attribute back to normal. These a_normal are constants defined in my curses.h. This is pdcurses. If we just go up here to the top, you can see it's pdcurses. And you can see there's other attributes in here for italic, underline, reverse, blank, bold, etc. If we, with this color pair macro, turns into the color attribute with the fiddly bits that specify which color pair I'm using. Again, provided by curses. I'm not doing anything in this example code that is specific to pdcurses to the best of my knowledge. I'm just using standard curses stuff. You'll see in here, there's, if I have debugging turned on, I got some little information that I dump out. I'm using the print W, so it's the scanf style. It's move print W, so go to position 0, 0, that's the upper left. Use this format string, format those values, and put them into the window. And then, because my formatted strings might be variable length, and I'm always putting them in the upper left, and I want the output to look clean, this final integer value here could go from 2 digits to 1 digit. And since it's a screen buffer, we're going to clear to end of line every time we write that information up in there, so there's not any garbage left over from previous output. So this redraw strategy, it works, but there's all this bookkeeping we got to do. And really, it's simpler. As you can see, it all fits on one screen. The scroll strategy, we just scroll the screen by -1, which is one line in the opposite of the normal direction. The normal direction scrolls text up. If you think about when we're using our shell window, and text scrolls up and new lines appear at the bottom. But if I scroll by -1, then the text scrolls down and I get a new empty line at the top, which is what I want. I'm scrolling my greeting the opposite direction to show you that it can be done, and not, I don't need curses to make text scroll up. I just printf and it just scrolls up. That's normal. So I can scroll in the negative direction by one line, and then figure out which line I want that I need to output next, and just add that in on the top. Because I scrolled by one line negative, which moved all the text down instead of up. So the line that was added that was empty is line 0. All the column and row indices are 0 based in curses. And I might have some extra junk, possibly, so we'll just clear to end of line to make sure that the stuff we added didn't have anything after it. So the scrolling approach is simpler. It requires less bookkeeping because we don't need to keep track of all of the lines that were moved. Whereas with the redraw approach, so in the scroll approach, I'm only adding one string to the virtual buffer every time I draw a frame. With the redraw approach, I have to draw all the relevant lines, right? So I have to loop over all the relevant lines and add each one. And again, clear out anything to the right that might have been left over from the previous frame. I didn't need to worry about the stuff to the left because I'm always indenting a certain number of blank spaces, so I didn't need to worry about clearing out anything to the left of the cursor. I just need to worry about clearing things to the right of the cursor after I put the string in. For the wide greeting, it's similar, but here my strategies are, so here's my string literals containing my sprite, and here my strategy is do it with a redraw or do it with a virtual pad. So let's take a look at the hard way to do it first, the redraw way. So let's see, what is my default strategy right now? My default strategy is redraw. Let's take a look at this. We'll run it again. Okay, so here's my first effect. And I'm trying to maintain a constant frame rate in my animation of 10 frames a second, which I do by using stood chrono to count the elapsed time. And then I call a function from curses called nap millisecond. It's like, it's not quite long enough to be asleep. It's a nap, right? You pass it the number of milliseconds you want to wait. You can do it, through stood thread as well. There's a way to delay for a certain number of milliseconds, but I'm using the curses function to do it. So that's how I'm able to achieve a constant frame rate on my effect, even though there's different amounts of work being done in each frame. My output is fast enough and everything here that, it's all being done in less than a tenth of a second. So we never get variable frame rates. But if we were going over a slow connection, we probably would get different varying frame rates because everything would be taking so long. Everything would be taking longer than a tenth of a second. All right, so if we look at the other strategy with the pad, what's interesting with the pad strategy is that I was able to... Okay, so here's the first effect. But with the pad strategy, I'm able to get a smoother scrolling from right to left. You may have noticed when we did the redraw strategy, the wide message appeared immediately on screen, completely on screen, but clipped on the right, and then it scrolled from the right to show you the remainder of the message. Now with the virtual pad approach, I'm able to scroll that in from the right so that it's, partially occluded, and then we get to see the whole thing, and then it scrolls off the left, and once it's completely scrolled off the left, it will start scrolling in again off the right. And so there it is. And if I press space, it'll pause. If I press S, I'm in single step mode, and every time I press space, it just advances one frame. That's just kind of a useful debugging trick that I implemented. Okay, so we got a smoother effect by using the virtual pad, and it's not because I couldn't code that scroll in from the right into the screen, and then it's always going to be clipped until it's always going to be partially occluded because it's wider than my screen. It will scroll in from the left and scroll in from the right and scroll off the left. I could have implemented that, in a fancier form of this manual redraw. I just didn't feel like investing the extra time to figure out the bookkeeping. So in the pad version, I've implemented these effects as instances of this pure virtual interface. So when this renderer is using the pad strategy, the constructor will create a new pad of the appropriate size. And if we have color support, we will set the current attribute on the pad to red, add the string to the pad, and then advance to the beginning of the next line in the pad by adding a new line character. And then after we've added all the lines, set the attribute back to normal. So when this effect is destroyed, we call delwin, which will destroy the underlying buffers that are held for the virtual space, that the virtual character space that represents the pad. and I am making sure that all my renderers are destroyed before I uninitialize curses, because this the pads and the windows and all of that, any extra resources that you explicitly create, you need to destroy those before you end curses, because it relies on the global curses data structures, which, if you call the end when first, those global data structures will be torn down before you tore down your dependent resources. So this is why I am explicitly calling clear on my little vector of up here, my vector of renderers, which I've held by shared pointer. I could have used, a set of curly braces scope here, but, I just thought it was cleaner to explicitly clear those. That's pretty much it. The rest of this code is just boilerplate for handling the keyboard interaction. As we saw here, I am calling getCH to get a character from the keyboard, and since I have set the standard screen to no delay, getCH will either return the character code or it'll return the constant ERR, which we can see is here. It's just a pound defined to -1. The actual value is not not specified in the API definition. You're supposed to compare it against ERR if you care. But it's either going to return a character code as an int, or it's going to return ERR, and I just compare against the character code. The bit of the achieving the frame rate is done inside this little function, get the current value of the clock. I am using the high resolution clock from Stud Chrono. So get the current value of the clock, render the frame, do some debug output, refresh the physical screen. Now we're all done with everything that needs to happen in the current frame, so I can compute a duration between now and the original time that the frame started, and just figure out, if I need to sleep for some time, if the elapsed time in milliseconds was less than the amount of time that I want to devote per frame, which is 100 milliseconds, which is 10 frames a second, then I can nap for 100 milliseconds minus however much time it actually took, so that when we're done after that, then 100 milliseconds will have gone by. So that's how I'm trying to achieve my constant frame rate. This approach, like I said, it works fine with, if you want to see what it looks like without that, we can just comment this out, run it again. Woo! It was over so fast we couldn't even read it. We didn't even get to, the window change happened. We didn't even get to see the first effect. Let's see if we can get that on the. Let's try it this way. Stop. Let's try run like that. Oh, yeah, went by so fast we didn't even have a chance to read it. So this little nap milliseconds in here is actually important. It's how we get the animation to be, humanly readable as opposed to machine readable. And that's pretty much it. I mean, curses, it's not that complicated a library. I showed you how to use a pad. I didn't show you how to use different windows, but the idea of different windows is just that you carve up the screen into discrete non-overlapping rectangles, and you create each rectangular area its own window, and then they can be refreshed independently. So you can have different portions of the screen updating at different rates. Because not all, if you have some kind of control panel interface and you've carved up the screen, you don't necessarily need to update the whole screen. You just need to update the different panels may be updating at different rates. Now, you might be thinking, what about overlapping windows? And baseline curses doesn't support the idea of windows that overlap and have some kind of Z order. There is a library in ncurses called panels that does support that, but basic curses assumes that if you have multiple windows, they are representing disjoint areas of the screen. As I said, it's a pretty straightforward API. This sample program will be up on GitHub if you want to look at things in more detail. The main advantage of curses is to not have to deal with the raw escape sequences yourself. You can just set the term variable appropriately for your terminal. These days, most of the time, it's xterm, or it's in Windows to use various Linux utilities that have been ported over, like the VI editor that comes with Git and stuff. You have to, fiddle around and find the right value of the term variable to set to make everything happy. But once you set it, it's fine. And that's pretty much it. If there's any questions, we can take those now. Okay, I don't see any questions, so we will end things there.